Hello and welcome to this session of the course Elements of Mechanical Vibrations. In the past we have discussed the methods to find out the vibratory response, the response characteristics of typical single degree of freedom, multi degree of freedom systems. However, the approach that we followed was restricted to limited number of degrees of freedom, and we had a lot of assumptions and approximations in place. So, we shall discuss some numerical methods in today's lecture. In particular, we are going to start with transfer matrix methods, out of which the simpler one, which is typically designed to solve a torsional vibrations problem, will be taken up first. Okay, now moving on, if we have many degrees of freedom and the system is almost distributed in terms of its stiffness and inertia properties, we now look at another alternate way of modeling and analyzing such systems. There are good numerical methods which exist for analyzing systems where the properties are more or less distributed, and then it becomes difficult to lump them and then use only few number of degrees of freedom. So, the boundary between a typical multi degree of freedom system that we have discussed in the foregone lectures, and this one is blur actually. I mean, there is a lot of overlap and there is no definite way to suggest that this system should only be considered as several or multi degree of freedom system, or when that same system can be modeled and analyzed using a numerical method. So, this numerical method is just another alternate choice that you have, particularly when degrees I mean the system size or its stiffness and mass properties are such that it is better modeled using a specific numerical method. So, one of the example that we discussed in our introductory video was this gearbox, which has several distributed gears and gear stages all along the shaft, as you can see. So, you will definitely wonder as to how many degrees of freedom should I consider in such cases. It will run in many of them, right? So, it is not going to be 2 or 3 or 4 or 5 degrees of freedom, it will definitely be in excess of at least 10 of them. The shafts also are having different cross sections all through. You can see that definitely the cross section of the shaft will continuously change and it would be varying at different locations. So, this is one example where you might like to model this as a system where properties are continuously changing. The other example is of typical steam turbine blades. So, these blades are arranged on the periphery of a disc, and those discs hold several of these turbine blades. One example of such a turbine blade is shown here, which pertains to one of the steam turbine. And if you want to model this as a vibratory system, it looks very odd to model this like a spring mass system with 1 or 2 masses connected, right? Even if you want to model this as a torsional vibratory system or a longitudinal vibration system, the modeling is not going to be very simple as such. So, if you see the cross section of such blades typically keep changing from the base towards the tip, and in some of the blades you will have a shroud which can be modeled like a mass at the tip. The cross section dimensions keep on changing along the length of such blades. So, all the properties which define the stiffness in the vibratory system, they are going to continuously change. So, we can't have only 2 or 3 mass elements to properly represent a turbine blade, and these turbine blades are very complex vibratory system, and an accurate estimation is in order. Okay, the approximation will lead to a very different, if not very different, but definitely not a correct frequency being evaluated. So the gearbox example that I showed here, you may keep on adding the disk depending upon the size of these inertia elements, and each of these cross sections of the shafts may be different. It may have even some steps could be expected within the two disks and so on, right? So all such cases will mean that we need to have a relook at the way we model such kind of a system. Now these systems, if we model using lumping of the inertia elements at regular intervals, that modeling approach will be called as the discrete system approach, where the entire mass or stiffness properties are lumped at discrete locations along the entire domain, and then we come out with some governing equations of motion for such systems. A cantilever like this may also be represented by modeling it like a distributed parameter system, wherein the mass and the stiffness property will be a continuous function of the variable x, which is defining its position all along the length. So those kind of models are called as the distributed parameter, where you can't discretize and then lump them at some discrete locations. So the numerical methods that we are going to discuss in this topic will actually model it still as a discrete system, but slightly different way. It basically still uses the basic static force balance equations and the Newton's law, but you will find that sometimes a complex system can be conveniently modeled rather than modeling the way we have been doing in the past. So one of the method that we are going to start with, which is comparatively a simpler one, and also can be a base for migrating to a slightly involved other alternate numerical methods, because this method will give you some good easy insight into the whole process of vibration analysis and modeling. So we start with the Holzer method, essentially designed for solving the torsional vibration problems, but going by the way it is formulated, you can also use it for the longitudinal vibrations or axial vibration problems. So it's a numerical matrix based methods for finding out eigenvalues, and the way it is formulated, we can't find out the closed form solutions by solving the characteristic equation. So being a matrix based method, we will have to resort to some numerical computational approach for finding out the natural frequencies. But then the advantage is that because the entire system is modeled like a matrix, then you can write a appropriate code, and then computers can take care of the calculation process. So going back to that gearbox, supposing that we have several such individual inertias connected by flexible shaft elements, and you can extend this to any number of such elements, right? So what we are basically going to do is we represent this entire system as an assemblage of individual segments. So I will discretize this or segment it into several such individual segments, and each segment has its own stiffness and mass property. Okay, so one such segment, for the sake of illustration, maybe I can take this as one segment. Okay, but you can as well take this small element as one segment, and then this as another segment, then this as another segment, and so on. So that way the entire system is segmentalized. You treat each segment separately, and that segment has, you know, that the vibration will happen only if you have a mass and if you have a stiffness. That means there has to be an element for storing a strain energy and an element for the kinetic energy. So what we do is, each segment will have a lumped inertia element and an element to to store the strain energy. So you have a stiffness and a mass or inertia element, and together will constitute a segment. And when you couple all such segments one after the other, you get the original system. That's the philosophy here. Now, if you make this as small as possible, the approximation involved in lumping the mass property, which is actually distributed throughout the length to one end of the segment, that effect will get reduced if you discretize this or segmentalize this into several segments. Okay, so you imagine that that segment is small enough, okay, to not let that segmentalization affect your eigenvalue estimation. Okay, but the more number of segments means more calculation, more computation. So you have to get a balance. Anyway, but this is the basic process that we follow, that we discretize this entire continua into small segments, and each segment has a lumped mass element and the remaining part is the stiffness element. Now, if this is to be treated like a torsional vibratory system, the gearbox which we saw, the majority or the more dominant vibration is going to be a torsional vibrations going by the torque transmission that happens in it. So what we are saying is that if this segment represents this inertia and this spring, the spring is essentially representing the torsional stiffness of the shaft, okay, that is going to resist the twist in the shaft. So this is the torsional stiffness of the shaft, and obviously when it undergoes a torsional vibration, this will represents the polar will represents its mass moment of inertia about the axis of the shaft, right. So that is basically how the inertia and stiffness elements define together one particular segment. Then you have another segment, and that way you can continue, right. Now let us focus on one such segment and look at how that segment's dynamics can be captured. So we take so this is segment number 1, 2, and then you can go right up to the nth segment, right, out of which let us say this ith segment is what you are seeing here. It has again as you see a spring and a mass comprising that particular segment. Now once those segments are defined, we further compartmentalize that segment into two parts, like there is an inertia part and then there is a spring part. So this spring is having a stiffness representing Ki, ith segment stiffness as Ki, and the ith segment's mass is captured through the inertia II, and this we call as the station I. The next subsequent segment will have its own station, and this will be I plus 1. The stiffness of this spring will be Ki plus 1. This will be the inertia element I plus 1, whereas this one will be of course I minus 1 and Ki minus 1 and so on. So on both sides you have interconnected elements. Now the state of the system at these specific locations will be quantified and represented by a state vector S. Okay, so the status or the state of this vibratory system at the location just on the right hand side of this inertia element, I am denoting that as represented by a state vector of the ith segment on the right of the segment, and In this case, we are defining the right hand side of the inertia part or inertia element, which is station I. On same lines, on the left of the ith station is a state vector is Li, which means the left of ith station, and then we can accordingly represent the state at the end of the segment, which now turns out to be on the right of the previous station, that is I minus 1. So we are attaching the name station to the mass element here. Okay. So to the right of I minus 1th station, the state vector is defined as SR I minus 1. Okay. Now state vectors will have its own state variables, which defines the dynamics. Now this being a torsional vibratory system, the two variables that will define are the twist and the torque. Okay. So the state vector is going to be defined by two variables, that is torque and the twist theta at each of these stations. Okay. So if I take ith segment's inertia, which is going to be assumed as a point inertia, in the sense that it has only the mass moment of inertia about the axis of the segment. Okay. What we are basically doing is, if the disk is included, you may ignore the inertia of the shaft and only consider the inertia of the disk which is mounted. Okay. But later on, if you want to consider this shaft itself as a one segment, then the mass moment of inertia of that shaft segments can be lumped here. So the parameters will be appropriately estimated based on what segment are you talking about. In this case, as an example, what we are saying is that this particular inertia represents that of the disk. So the disk has its own mass moment of inertia about the axis of the shaft, and that is represented by II. Now on the right hand side of this station, we said that there is a state vector S on the right of the ith station, and this state vector is on the left on the left of the ith station. Okay. So these are basically the two state vectors that we have defined. So the state vector on the left of ith station is in terms of its twist and torque values, and so for the spring element, which defines the torsional stiffness of the shaft, this the torsional stiffness of the spring, and of course of representing that of the shaft, has two state vectors on both ends. So this state vector is on the left of the ith station, because here comes the mass. So this state vector and this state vector, they are actually identical. I mean, it represents the state vector at this location, and that is SLI, and this state vector is also SLI. Okay. There are the torques which act on both sides of the inertia element, and of course on the two ends of the spring element. Similarly, there is a twist at this point or this location, and there is a twist here, theta r I minus 1, and together the torque and the twist define these two state variables define the state vector. That is very simple and straightforward process here. This will continue on both sides. So you will have similar elements on the left hand side, similar elements on the right hand side. Now the question is, having defined these state vectors, we would obviously like to establish a relationship between these state vectors. When the whole system vibrates, okay, then how are these state vectors relating to each other? That is our job to establish. Now let us focus on the inertia of the segment, right. So when you have a disc um, connected to the shaft element, and out of this segment which was defined as a spring and a mass, we are now trying to focus only on the mass element, and the mass element is like a disc, okay. Here on both sides of the disc, on this surface and on this surface, there would be torques and twists that will happen, right. So theta, let's say if this is the disc number 2, so I am basically taking an example that this is, let's say if it is a disc number 2 and segment number 2, so this is going to have inertia which I can write as I2, and the twist on the right side of this inertia is going to be theta 2 r, and the corresponding torque on the right hand side is T2R. T2L will act on the left side of it, and the twist on the left hand side will be equal to theta L2. That is how it is going to be. These two opposing torques are going to keep this in equilibrium, okay. But the disc is an inertia, so in a dynamic condition during your vibratory motion, the disc is going to have its own inertia, right. So again we apply the Newton's law and try to figure out the relationship between these state variables. So what we do is, the net torque across the disc should be equal to mass times inertia, okay. So I2 times theta 2 double dot is going to be equal to all the net torque which is going to act on it, okay. So T2R minus T2L will be equal to I2 theta 2 double dot. That is the straightforward simple dynamic equation that we have here. So now what we say is that this entire system is vibrating in a harmonic fashion, so that the response theta 2 can be represented as theta 2 cap, which represents the amplitude, times cos omega t. That is a harmonic solution that we are assuming. Now we know that what we are going to do is to arrive at eigenvalue estimation. Now when we say we are wanting to find out the eigenvalue, at any of the eigenvalue, the entire system, be it segment 1, segment 2, segment 3, segment n, all these segments are going to exhibit or follow or go through a principal mode or normal mode of vibration, wherein all the elements are going to oscillate at the same natural frequency. It is not going to be like segment 1 vibrates with the first natural frequency, segment n vibrates with 10th natural frequency. It does not happen like that, right. So when we are assuming a principal motion, assuming that there is a harmonic natural mode vibration that is taking place, then theta 2 cos omega t represents the harmonic vibratory motion. Now when that happens, theta 2 double dot can be shown that this is going to be minus omega square theta 2 cap cos omega t, which actually means equal to minus omega square theta 2. Theta 2 is basically time dependent twist. If this is true, then we can substitute it back into the equation which was our governing equation, and then assume that the disc is rigid. That means there is no relative twist between the two faces of the disc, right. The disc is rigid enough that all the strain energy is stored in the spring, which is the shaft. The disc does not store any strain energy, it only contributes to the kinetic energy. With that logic, then on both sides of the disc the twists are identical. That what it actually means, that if you have another shaft here, then the twist in this left end of this shaft is going to be same as the twist on the right hand end of the previous shaft, and across the disc there is no relative twist, okay. So theta 2 L is equal to theta 2 R, and then I can write these two equations in a matrix form. You can show that this theta 2r is equal to theta 2l. So you have only one diagonal element here, because theta r is not related to the torque quantity, and therefore it will have, the first row will have only one quantity, I mean unit value at the diagonal location. Whereas this expression tells us that T2 and T2R and T2L are related through this particular term. So I can write T2R, which is the second value in this vector, equal to minus omega square I2 into theta plus T2L. So that is basically this T2L. So you can show that this equation and this equation can be written in a matrix form by which is represented here. And what are these theta and t? These are all the state variables. So the state vector on the right side of the inertia element, this is ith inertia, on the right side is related to the state vector on the left side through this equation, okay, and it is related through this matrix, which is this matrix. State vector on the left and state vector on the right of the ith segment, in this case second segment, second disk, is related through this matrix, which is called now a point matrix, okay, because we are considering that at that point only inertia contributes, there is no strain energy stored. So it is a point matrix. The entire mass of the shaft is lumped at the disk location if the disk was not there, okay. The disk is there, so you can lump the mass or the mass moment of inertia of the shaft also to the disk location, but that is a point matrix Pi. Its elements are all given here, omega square I2. Okay, now basically what we have been able to do is to relate the right side of this ith station to the left side of the ith station. The relationship between these two state vectors is established through this point matrix. The job now is to complete the remaining part, because this represents one segment, right, and there are multiple plenty of segments to come before that and after that. So let us figure out now, how do I relate this state vector here to this state vector? What would you call this state vector? It is going to be right of I minus 1, because I minus 1th segment will come here. And this state vector will be the right of this rth I minus 1th mass element, okay. Okay, so in that case what we do is we now, this is already taken care of, we are here. We are now trying to relate this part with this state vector with this state vector. So what we have is massless spring element. The shaft here is considered massless, it only stores the strain energy. So whenever it undergoes a twist on across the two ends, it stores the strain energy. We would like to look at the force balance in that case. So what is going to happen if the torque is applied here, and that will be resisting torque on this side, the torsional stiffness, if it is characterized by K2, then we can write a force balance. Now this is a static force balance. So the torque twist relation, we all know that the torsional stiffness will be given by torque divided by the net twist in the shaft, that is theta 2L minus theta 1 R, because this is now going to be theta, if this is a second disk number 2, then on the, there will be another disk here which is disk number disk number 1. So this is going to be theta R1. The previous disk will be disk number 1. So on the right side of that disk number 1 will be theta 1 R. So just like the torque on the right side of that disk is going to be T1 R, right. So T1 R and T2 L, they are going to be identical. It's a single force, two forces, the two torques on the same beam, that is the same shaft which is applied. So the two should balance each other out. So T1R will be equal to T2L, and then divided by K2 will give you the net twist bit in the shaft bit across the two ends of the shaft. So theta 2 and theta r are related like through this expression. So as we said, T1R is equal to T2L, and now these two equations together will lead now this equation. So obviously T2L is equal to T1R, and theta L minus T1 sorry theta 2L minus theta 1R, this left hand side, is equal to 1 by k times 1 by k times T1R, and that's how you get this particular matrix equation. Now this matrix, unlike so this number 2 represents the second element, right? So element number 2, that's what we are assuming, that let this be the second part of the total assemblage. Now this particular matrix, in contrast to the previous matrix that we derived for a point inertia, this is called as a field matrix. It represents the entire shaft element storing the strain energy. So this is represented as F, that is called as the field matrix, and it relates the state vectors on the left of the next element to the right of the previous element. So that is how the right of the previous element and the left of the ith element, that's how it gets related, like as you can see. So the general expression relating the two state vectors is given by the field matrix. Now what we have is that our segment was this segment, which we subdivided into inertia part and the stiffness part, and then we just got the relationship between this state vector and this state vector through a matrix called as a field matrix, and therefore SL I was related to SR I minus 1 through this field matrix, and we already got an expression for the relationship between the state vector on the right of the ith inertia to the left of that inertia through the matrix called as a point matrix. So these two are the matrix relationship between the state vectors is what we have. Now let's club them together so that it represents the entire segment. And it is quite simple here, because you have a state vector SLI here. If I replace it by this, what can I get? I will get the state vector on the right of the ith segment related to what? So on the right of, okay, so right of the ith segment related to right of SRI related to SRI minus 1. So the entire segment is now related through the end state vectors. This is what I have. Now the job is to go one more step beyond. You have got everything defined across a segment, so you have many segments coupled to each other. You keep on writing them in terms of the state vectors of the previous segment, right? So that's how you will ultimately what you will get, Sn related to S1 or S0. That's what will happen. S0, why? Because the extreme element state vector will be on the right of the previous one which doesn't exist, so we call it as 0. Okay. So it relates the state variables between the one station to the next station, and then it will have two parts. Obviously we discussed all of that it will have a point matrix and field matrix, and that's how we showed that together the product of this point and field matrix is going to be now called as the transfer matrix, capital T. So transfer matrix here is a product of the point and field matrix. Okay, make sure that you you use them in the same sequence, point matrix followed by the field matrix. Their product is going to give you a matrix called as a transfer matrix. Therefore, these methods are called as transfer matrix method. Okay, so this transfer matrix is, if you multiply using all the individual elements that we found for P and F, the net product is going to turn into like this. So, the matrix of the ith segment is going to be 1 by k minus omega square I, 1 minus omega square I by k. So, k is basically the stiffness of the shaft element, and this will be for the ith segment, and it will relate this state vector with this state vector. Yeah. Then, as we discussed, what we are supposed to do is now keep on adding number of segments, and how we do that, because as a general expression which we have seen earlier, which is SIR is related to SRI minus 1. So, the larger segment gets related to the previous segment. So, therefore, S1R will be related to S0R, the previous segment's right side, through the first transfer matrix. So, now if I call this as S0 and this one as S1, of course, the right side of it. So, S1R is going to be this state vector and S0R is going to be this state vector. They will be related through a transfer matrix T1. Similarly, S2R will be related to S1R through the transfer matrix T2. That is how you get, and so on. So, I can relate this S3R through the transfer matrix relating here by T3 and so on. Okay. And if you keep doing that, SR nth segment will be related to the SR 0th element, 0th in the sense that there is nothing here. So, this basically represents the extreme state vector. It actually is now the product of all the transfer matrices, because this SR1 I am going to replace by this transfer matrix. So, on the extreme right hand side you will have T1, then followed by T2, and then followed by T3 and up to Tn if you have n segments. What happens? You basically will have to now keep multiplying all of these transfer matrices. Ultimately, this state vector will now get related to this state vector. So, Sn will get related to S0 through a transfer matrix which is going to a product of Tn, Tn minus 1, Tn minus 2 up to T1. This entire matrix, if I call that as an overall transfer matrix U, that matrix will relate these two state vectors. Tell me, what is the size of this matrix T? What was the size of the field matrix? 2 cross 2. What was the size of the point matrix? Was it different? That there are only 2 state vectors, 2 state variables. The point matrix was 2 by 2, the field matrix was 2 by 2, their product will be again 2 by 2. So, the transfer matrix is 2 by 2. Now, each of these transfer matrices for each segment are simply getting multiplied. So, 2 by 2 multiplied by 2 by 2 multiplied by 2 by 2, irrespective of the number of segments that you discretize it, ultimately the overall transfer matrix is going to be still 2 by 2, right. There is a catch here. So, the state vector here is going to be theta and torque related through this overall transfer matrix to theta and torque at the nth station. Okay. So, this is a 2 cross 1 vector, this is 2 cross 2 matrix, and this is 2 cross 1. Okay. What is the problem here? Okay, we will get back to that problem after we actually show that this overall transfer matrix will be a product of individual transfer matrices. Now you can see that this individual transfer matrix, what are the elements of this individual transfer matrix? It is the stiffness, torsional stiffness of that segment, and the inertia property, right? Now this K and I, these are all the properties that you will be anyway knowing your system. In that gearbox, you know each gear in its dimensions, the material properties and all. So you know the inertia value of that gear, and the shaft connecting to the next segment, you know the dimensions of the shaft, so you know the stiffness of the shaft, knowing the material properties. So that way I and K is known for your system. What is this omega square? What is that? It's a assumed eigenvalue. It's the frequency with which this system is going to vibrate. The whole purpose of yours through this modeling is ultimately to reach to that value, right? But if you are defining your state vector here in terms of this overall transfer matrix, which is going to be product of all of these into the last state vector, you do not know this numerically, isn't it? You don't know that numerically. So to show that this u is going to be something similar to that is going to be a problem, because there will be n of them, and every time it is going to lead to some expressions. It will lead to something similar to your characteristic equations of big polynomial. Makes no sense to solve it, right? Or formulate even. What we do is, let's look at one simple practical system, like the same gearbox is connected to a huge flywheel on one side, let's say, as an example. In the case of a cantilever, it gets routed to the disc, so one end of it is fixed, provided that you model each of these segments as individual, having its own torsional stiffness and inertia. But this is another example of the gearbox that we saw. Suppose one end is fixed to a big flywheel and then the other end is free. Now if you look at the state vector at the station 0, that's here is your state vector S naught, and here is your state vector Sn. It has its state variables theta and t. Can we say that the flywheel being so heavy, we can treat that end condition to be fixed end condition? We have seen that in a vibratory system modeling, simplifying assumptions could be that if the inertia of the flywheel is large enough, we can treat them to be almost rigid. If that is the case, the twist there will be 0, right? But the torsional dynamics of the entire gear train is going to generate the twisting moment at the root, just like there is a fixing moment and a shear force generated by the vibrating cantilever at its root. So torque is not going to be 0, but the twist can be assumed 0. So those are called as the boundary conditions here in this example. So S naught can be defined in the form of 0t. The state variables theta take the value 0 and t is a non-zero value. What can you say about Sn? What will be the state variable at this extreme end? Can theta be 0 there? A free end, you can't expect that to be 0 at all times. Okay, so that theta cannot be 0. So there will be some non-zero theta value at the free end. When it vibrates, it will twist, it will move. What about the twisting moment or a torque at the free end? At the free end, it's a free end, so there is no torque acting, right? That is going to be 0. So now you have Sn to be formulated with torque being 0 at the free end, and you have theta and 0 as the two state variables defining the station n. Now we already have a relationship between Sn and S0. What was that? Sn is the overall transfer matrix S0, right? Now assume that your individual transfer matrices T1, T2, T3, T4, all of them are suppose numerically known. Finally, when you multiply, you will get what? U11, U12, U21, U22, right? State vector on the n and 0. This is how they get related, right? How you get these is something which we see later. But supposing that all of them are known, you multiply and you will get these 4 elements of the overall transfer matrix. Now, in this particular example, when Sn is written as theta and 0, and this is written as 0 and t at station 0, can I write that from the second equation here 0 is equal to U22 into capital T? Can I write this? And T means T0, isn't it? Now, when will this particular equation be 0? At all times. Please make a note that this has to satisfy at all instants of time. It's a dynamic system. It is only possible because t at 0 means fixing moment cannot be 0 all the time. So, the only way for this equation to be satisfied and true for the given boundary conditions is that U22 should be 0. True? Okay. So, that means you have this condition that U22 should be always 0, a condition to be satisfied, and now because of the fact that all the transfer matrices are a function of omega, we can't know the individual elements of any of the transfer matrices numerically because omega itself is unknown. What we now try to do is assume a value of omega and check. Suppose this entire gear train, we take a rough estimate that okay, it might have a value of 35 hertz as the first natural frequency. So what I can do is I can start with 5 hertz onwards. My experience tells me that it cannot be less than 5. I can start with 5 hertz, 5 hertz or whatever radians per second that turns out to be as the starting point. I calculate it for 5, right? What will happen if I use 5 as a first estimate of our omega? Using this, I find out what is T1, because once I know omega, all these transfer matrices are all known. All these transfer matrices are all known because I know K and M or I for all the stations. What was unknown was omega, so I assume that omega, okay? And then I find out all the individual transform matrices, multiply all of them and just find out what is the value of this particular element. I do not care about what is U11 and U22, U21 and U12. I do not care. I only focus on U22. Okay. And that method is called as a root searching method. So, I assume first I will start with this omega value, the lowest that I can think of. I find out maybe U22 value. For this it turns out that U22 is this, then I increase the value of omega, figure out that okay it is this, then I increase it further, I figure out that it is this, then I increase it further, I figure out that the sign has changed of U22. The moment sign changes, I can increase this omega by a slightly lesser delta omega value and then basically search the value of omega where the sign change happens. That is the root searching method, but this is numeric, so it is an iterative process. Okay. After this happens, then I keep going ahead, maybe I will get another sign change and that will be in my second natural frequency and so on. Based on the boundary conditions or end conditions, I only have to figure out what should be the element that must be 0 at all times for this to be exhibiting a natural mode, normal mode of vibration. Okay, but the product is only 2 by 2 matrix, so it is easier to handle, right? Now you may see this in the context of other numerical methods. No, if you have a very complex system, depending upon the amount of discretization that you do, for 100 segment you will get some number of some size of the matrix. If you take it to 20,000, the size will become much bigger. But here the same shaft in a torsional mode, if you are discretizing it into 10 segments, or if you discretize into 10,000 segments, still the matrix is going to be 2 by 2. Okay, number of segments will change the number of computations that you have, but that also can be that can also be reduced by with the fact that we are not at all concerned about U21 or U12, only U22. So your calculations can also be somehow reduced in that sense, if you carefully plan for it. Not all columns and rows needs to be multiplied to get U22. Anyway, so the point is, you can go through this brute force method of searching the roots. Once the roots are searched and you know how much is the value of omega, then everything gets completely defined for you. So again, the polynomial is going to be what? It's going to be huge. If your number of segments are more, this entire polynomial is going to be unmanageable, just not possible. That is why instead of using a classical method of discretizing, writing governing equations, we are resorting to this numerical method, where you only need to have these matrices defined, and then you are good to go. Now what can be done by you is that same system, if you discretize into, let's say, 10 segments, find out what is omega 1, maybe you will get omega 1 this. Then instead of 10 segments, that entire gearbox you discretize into 20 segments, reevaluate omega 1, maybe you will get this value. Discretize into 25, 30 elements, maybe 30 elements, you will find that's larger number of segments, this omega 1 will stabilize and will approach a constant value. So you then decide what is your tolerance value, what error you can tolerate for the first one. Typically people do it for the first 5 eigenvalues, depending again upon what is the rotational speed of your crankshaft, sorry, the shaft of the gearbox. What frequencies are you interested in? The highest of that should not be having a large error just because you are discretizing it into a smaller number of segments, because the larger the number of segments, the computation increases. Now suppose that the gearbox is not fixed to the flywheel, right? That means it is free, no restraint, right? Now in this case, instead of U22, there could be some other element that you need to find out. So what will you do? Here torque is 0 on this side, torque is 0 on this side, free sides. Now obviously there is no external torque applied, so the torques are actually 0, a free system. And if that is the case, then you know what will happen. U21 will be 0, and then the same process will apply. Figure out where the roots are crossing and changing their signs. So to find what element is to be 0 is like finding out your characteristic equation. Okay, and once it is done, then it is again a numerical process of getting the regaining eigenvectors, eigenvalues. Now will be interesting, how do I find the mode shape? This is only one part, getting eigenvalues. Okay, we still haven't really discussed about the damping part of it. In this case, we are interested only in eigenvalues and eigenvectors. Now how do you find? So if you consider fixed free system, suppose This is our equation, right? This is our final equation that we got. So what I can do is I can write or assume theta n to be unit value. Ultimately, eigenvector is what? Relative to one particular deflection, how other elements are deflecting with respect to that, in relation to that, what is the relative displacements or deflections or deformations in the system, vibratory system. That's what our eigenvector is all about. For example, if the shaft is flexing with respect to this, if this is treated as maximum 1, then how much is this, how much is this, how much is this, is that is basically your mode shape. So what we do in this torsional vibratory system, we say that at the end, there was a flywheel here and then there were so many elements here. At the end, what we say, if this deflects theta equal to 1, in relation to that 1 unit twist, what are the twists in the rest of the elements? So when we assume this theta at n equal to 1, we still do not know how much is this value. By solving the equation, what you get, u11 into t, sorry, so u12 into t is equal to 1, isn't it? If you take the first equation, 1 will be equal to u12 into t naught. So t naught will be how much? 1 upon u12. Now please make a note that you have already done the estimation of the eigen value. That means you already know what is omega. So all the values of u12, u22, u21, everything is known. Once the frequency is known, all the transform matrices are known, all the overall, all the elements of the overall transform matrix is also known. So you know how much is T naught. Okay. Now in the fixed free condition, this theta was equal to 0 and torque was not known, which was T naught, which you have now found out to be 1 by u12, which actually means that the state vector here is completely known, right? So state vector at the flywheel or a fixed end is known. This state vector S naught is completely defined, suppose, because you have T naught known and and theta at 0th station is 0. So the state vector is 0, 1 upon u12. Once one state vector is known, these are so simple and straightforward, because you know the relationship between one state vector to the next state vector. So theta t1, that is the state vector at the end of the first segment, is related to the previous segment through this transform matrix, where for the first segment omega is known, I is known and k is known, and this is completely defined as I said here. So that means your theta t1, that means this state vector S1 is known. Once S1 is known, S2 is known, S3 is known, and so on. You can keep on making these multiplications to get all the state vectors known. Once all the state vectors are known, for mode shape you don't care how much is the torque acting at each element. You are only interested in thetas. So you can plot now that if the theta twist here is 0 and here you have assumed it to be 1 unit, how much is the twist in the rest of the elements. By knowing this twist value, this twist value, this twist value, and so on, all these twist values are known, this becomes your mode shape. You take omega 2, probably second omega, maybe this will be your mode shape, and so on. So first root searching method will give you all the eigenvalues. For each eigenvalue, using this process you can find out all the eigenvectors, corresponding eigenvectors, but all of that is numerical, numerical approach. There is no closed form solution. So that basically will give you all the elements of the eigenvector, right? So this is the way it is to be evaluated. So, the summary of this lecture, we discussed today one of the numerical methods. We got introduced to a transfer matrix method, and in particular the Holzer's method for torsional vibration. These methods allow us to discretize the continuum into many number of segments. In this context, in the Holzer's method, we also understood the root searching approach for locating the eigenvalues. Based on today's lecture, these are some of the review questions. And these are of course the answers.